So, welcome to the video cast or the vodcast for special relativity. We're going to start this unit by talking about position and velocity within the theory of relativity. So, the big idea for this unit is time is not absolute. And what that essentially means is when we studied kinematics, we looked at equations that describe motion. And in those equations, we talked about time intervals, or delta t. Now, before Einstein developed the special theory of relativity, everyone assumed that the time interval must be the same for any observer, whether that observer was at rest or in motion with respect to the event being measured. So this idea that time is the same for everyone is what we mean when we say time is absolute. The theory of relativity, however, tells us that time is not absolute. So before we get started, we're going to want to talk about or do a bit of review of our vocab from previous units. So we'll talk about inertial reference frame, position, velocity, relative position, and relative motion, all of which are key ideas for us to understand Einstein's theory of special relativity. So the first thing is an inertial reference frame, and the word inertial comes from inertia, or that idea that all mass has inertia. The property of inertia being an object's tendency to not want to change its motion. So an inertial reference frame is a frame of reference that is at rest or is moving at a constant velocity. So everything that we've looked at in this course so far has been measured in an inertial reference frame, and that reference frame has been the Earth. So when we're taking measurements of motion or position, for example a car, we've always talked about its velocity or its position in an inertial reference frame. And we've always said that that inertial reference frame is the Earth. Other things we looked at were how planes travel, boats, and trains. All of the things that have motion we've measured with respect to the Earth, basically just meaning that the Earth is our inertial reference frame. Now, you might be wondering, but the Earth is moving. Well, that's true, and we usually discuss its motion relative to the Sun, and so the Sun becomes the Earth's inertial reference frame, and so on and so forth. So, for our purposes, we can assume that the Earth is staying still, and it is our inertial reference frame. Now, the other idea we talked about is position. So here we have a position here as our origin, and time passing. So in this situation we have the position is not changing for the first 2 seconds. So the position changes in the negative directions. That could be left or down. Here, whatever this object is turns around, heads back towards the origin, passes the origin, and then stops. So you can see for this time interval here, the position has not changed. And then at 13 seconds, the object heads back towards the origin, and then away from the origin in the opposite direction, turns around, heads back, stops, and then back towards where they started. So that's position, which is very similar to velocity. So our velocity, here's another position time graph. Our velocity is how fast is that position changing. So you can see over the first 2 seconds here, we have gone from 0 meters to 4 meters. So we have traveled 4 meters in 2 seconds, which means that we have moved 2 meters every second, and that's our velocity. The velocity here has changed. The slope is smaller, so the speed has lessened. At this point here, the object turns around and heads in the opposite direction. Our position is getting less positive, or we're heading towards the origin. Passes the origin, continues on here, and keeps moving in the negative direction. So all of this has been reviewed so far. Now, let's just look at relative positions. Throughout our previous study of motion, it's become clear to us that an object's position and velocity depend very much on what the observer is doing. For example, a bird flying through the blue sky is either above you or below you, depending on where you are. So if you're on a bike, the bird is above you. However, if you're standing on the top of a cliff, the bird is below you. Relative to you, that bird's position changes. Now, relative velocity carries on from this idea. If you and the bird are heading towards each other, your bird is moving relative to you at quite a rapid rate. If, however, you and the bird are moving in the same direction at the same rate, according to you or relative to you, that bird has no velocity. It's not moving relative to you. But what about time? Let's do a thought experiment, and let's say that you're scarfing down a plate of fries, and two people are going to observe you and time how long it will take you to eat those fries. For a long time, intelligent people thought that both observers would record the same time interval, no matter where they were or what their velocity was. But this is wrong. Einstein did some thinking at the turn of this century and showed how the two observers could record different times for your fry eating. He came up with two postulates. The first postulate, or principle, is the relativity principle. The relativity principle basically states that the laws of physics are the same in all frames of reference which are moving at a constant velocity. And as we looked at before, that would be an inertial frame of reference. So this is basically repeating what Galileo and Newton had said before him. Nothing new here. So as long as you're not accelerating, the laws of physics are the same everywhere. Now, there's a subtle point here. Let's do another thought experiment. Let's say you are in a train on smooth, frictionless tracks, so there's no wobble, and the window is closed. Can you think of any experiment that would allow you to determine whether you were at rest or whether you were traveling down the tracks at a constant rate? So right now I want you to push pause on this video and answer the question in the box that you'll find below this in the Moodle site. Okay, so you might have actually had a difficult time thinking of an experiment that would actually show whether or not you were moving. And there's a good reason for that. That's because there is no experiment that you can do that will show you whether or not you're moving. Each frame of reference is equally valid. So all frames of reference are equally valid. Einstein's second postulate is the principle of the constancy of light. And that is the speed of light is the same for all observers regardless of their velocities or the velocity of the source of light, which basically means that everybody sees light traveling at the same speed regardless of their own motion. And so let's go back to Michelson and Morley. Michelson, Morley, and other researchers of the time were doing experiments to measure the speed at which light travels, and they were getting some strange results. Their experiments were indicating that it didn't matter whether the source of light was coming towards you, moving away from you, or staying still. The light from the source always came towards the observer at 3.0 times 10 to the 8 meters per second. Now, you're probably thinking, if a spaceship is coming towards you at half the speed of light and it turns on its headlights, the light should be coming towards you at 1.5 c. But in actuality, that's not what happens. It still approaches you at c. The speed of light is the same for all observers, regardless of their velocity. So Einstein combined these two postulates, that the laws of physics are the same in all inertial reference frames, and the speed of light is the same for all observers in an inertial reference frame, and he came up with some very interesting claims. And those are the claims that we will discuss in further videos.